How does the system sound? Okay, thank you for coming, staying with us. We are continuing our chapter on density functional theory. Last time we have acquired the simplest possible foundation of density functional theory, and today we are starting to go into actual theory that is being used. So let's focus on what is on administrative side first. So I promise to put on D2L the little handout very related to today's lecture, almost 90% overlap. I have designed very simple, much simpler than the previous one, homework, which is basically answering verbal in verbal form. Yes, I agree. No, I disagree. Yes, the theorem is correct. So we are going to have a lab today at 6 p.m. and there it will be a continuation of our previous lab. When we met a week ago, we learned how to prepare input files for new software, for VASP software, and today we will practice how to extract some basic forms of output. Basic output. And sometimes later we will try to share our experience on this basic things from last time, basic things that we will be covering in the lab today. And there will be, I think, 2 labs more on advanced topics. But I think those are not challenging. We are just getting experience and sharing what we learned. So last time we were talking about electron gas, where electrons don't experience much of interaction with ions, and some strange universe that doesn't have any nuclei, any ions. And our plan to acquire the steps towards density functional theory can be formulated as having background in some definitions. Then we need to spend a little time on theorems because they are integral part of the. Yes? Is it better? Or not really? Right. Is it okay? Okay, so there are some theorems, and they're not used in software, but they provide some legitimacy to the theory, and they explain why one can expect useful results from so simple theory, simple in respect to other alternative theories. Then there are practical implementations of DFT. And there is a way to use it to compute observables. So last time we are done with background. Today we will try to cover definitions and part of theorems. Actually, there are 2 of them. And we need 2 or 3 lectures more to cover practical implementation and observables. So let's just recall what we did last time, we were splitting whole space into boxes. Box number 1 is density here, number of electrons in box, and the volume of the box. Box number 2 is density from number of electrons here divided by volume of the box. And the whole universe is split in such boxes. So electrons, their number of electrons obey the Fermi-Dirac distribution. And the total energy of such universe filled out with electrons can be expressed as summation over all boxes, density in each box in the power 5 over 3 is some constant. And if we have infinite number of boxes, we just replace it by an integral. So in this theory, one takes into account only the kinetic energy of electrons and fact that they obey Pauli exclusion principle and they follow the Fermi-Dirac distribution. The main take-home message that there are procedures that do connect total density of electrons. This density depends on the position. It is different in different points of space. It's the total energy of the system, which looks helpful and beneficial. And the whole goal of the density functional theory is to develop similar law that connects density with energy, or more realistic universe. So the universe that do have ions or electrons actually interact with each other. It will be the final expression will be a little more complicated. We even are not going to write it down. It will take longer, several lines, and we will just refer to it. But it does exist. Okay, so it was a review of last lecture. What is functional? Just give me some sign if you know or you do not know what it is. Okay. Can you switch on the microphone and
functional is an operator that acts on a function, right?
Okay. Good enough.
Okay.
So usually in basic calculus we have functions or operators that do convert a number into a number. And if we establish correspondence between a function and a number, we have something distributed, something that has several values, but we convert it into a single number, one can define it as a functional. And some convolution, summation, integration, because we need to get one number out of several. The simplest example, probably if one makes a budget and has several items, and then there is a total. So total is a functional of the budget, because you add together all things. Okay. Yes, you can say that they are. You can refer to them. Well, there are different. We are not discussing right now what is the specific form of the connection between a function and a number. There is some way to connect function to a number. So we need some examples. One example was on the previous slide. Another example, if we live in Hartree-Fock theory and molecular orbitals, then we do have molecular orbit. It depends on position. And if we take conjugate and multiply it by itself, then what do we expect to get? Yes, I see some signs that we should get 1 if it is a good function, it is normalized and defined in the right way. So we get 1. So this one is a function, and this one is a single number. So it is just procedure of normalization is one of the examples of the functional. Example. Okay, there is a practically interesting and important definition of total electron density in respect to Hartree-Fock theory. So if we do have this operation, normalization of the orbital number I. Then the by making summation of all orbitals conjugated, we are obtaining the probability that one can find an electron in the place of space R, or on the language of density functional, the number of the density of electrons in the point of space R. And if you decide to integrate this thing over the whole space, then we are getting the integration of each of the terms here. First term gives us normalization of the first function. It will be 1, right? Because first function is normalized. First molecular orbital is normalized. Then we do integration then we do integration of the second orbit. It is also normalized. We also do. Then each of the orbitals is normalized, and we do it as long until we reach the last occupied orbital. So we get as many ones, as many electrons, we do have in the system. So 1 plus 1 plus 1 will be actually this number of electrons. So it is another example of a functional. So total number of electrons in the system is a functional of the total density. Does it make sense? Total number of electrons is a functional. Highlight that it is functional of the total electron density. Okay. So on the next slide, we are going to acquire a little of terminology that was originally used by developers of this density functional theory. And this terminology refers to molecular Hamiltonian, to the molecular Hamiltonian for the to the electronic part of molecular Hamiltonian that we are solving for 75% of our course, or except the first few lectures. So we do have kinetic potential energy of interaction with nuclei and potential energy of interaction between electrons. And the designers of the theory, they went really non-trivial logical way. They considered, okay, electrons is our primary goal. We are interested in electrons. We are making a theory for electrons, and it is our main thing. Everything except electrons is some perturbation, is some impurity that makes things not so nice and simple as in Thomas Fermi, in electron gas. So everything that comes outside is external, is foreign, is, well, not desirable, but it what makes complications. And here in this expression for electronic part of molecular Hamiltonian, the kinetic energy refers only to kinetic energy of electron. Right? It depends only on either wave function or density of electron. The electron interaction also depends only on electron. And the only term that refers to something perturbative, something that comes outside, is this potential energy of interaction with nuclei. Right? So we can write it down as charge of an nuclei and the distance between an electron and nuclei. And then we make a summation over all nucleons. It is this little. So we need distances like this from electron number 1 to ion number 2. Say. Then we take an inverse of it and put minus sign in front. And then this attractive potential is added together for all electrons and all ions. It is not scary. No, it's Coulomb attraction. So since it is not a natural property of electrons, since it is something external, it is really verbalized. It is referred to as external potential. I'm not a big supporter of this term, but all literature uses it, so we better agree on using it at least for this chapter. Okay. So here is first of the theorem, and we will be dealing with it until the end of today's meeting. So this brave gentleman, Hohenberg and Kohns, made an effort to prove that in case one does know total density of electrons for ground state, then it is enough to determine the external potential and the total energy of the system. For the density does determine total energy. It is very similar to Thomas Fermi theory. It is similar to electron gas model that we considered on last lecture, right? So by integrating density with some power, we get total energy. But it is only if there are no interactions. But this part of the logical chain looks crazy. It is very non-trivial. So usually we are thinking that when we put positions of ions in our models, it is an input. It is something that determines whatever we get as an output, right? So when we do practical calculations, we start with building atomic models and we feed positions of ions into a code. And as a result, we get energies, densities, orbitals, whatever we need, observables. But here is, I wouldn't say corrupted, but inversed logic. So they're thinking that if from somewhere we get a density, we can find a potential, and therefore probably we can find even what are the positions of ions. So they're trying to probably make an analogy with criminal investigations, when fingerprints make a trace, make a reflection of what actual finger of a person is, and based on the fingerprint one can identify what was the original person who was touching the surface. So here it is the same logic. So this one, external potential, is to some sense is a fingerprint. Yeah. Density is a fingerprint. And by looking, so when we place ions in the model, they determine in which spaces, in which areas of space, in which localizations electrons are most comfortable to reside. And so ions determine potential, and then this potential determines where electrons are residing. But if we look backward, if we have the final product, if you have density, it is maybe enough to reproduce, to reconstruct which potential was responsible for their distribution in space. And maybe even enough to reproduce where were original ions placed. And this idea is the basic of the theorem, and later they do a little rigorous effort to prove it, but the idea is that density determines observable. Okay, so we are going through the proof, and before we start, I will try to practice memorization and reproduce what should be in these blocks. So we start with an idea that density, defined in each position, determines the potential of interacting with ions, the external potential. And we should get proof that it is indeed so. From density, we get the potential and the total energy. So the proof bases on two concepts. One concept is the wrong assumption. So we are going to assume that in a logical way that initial statement is not correct, and then arrive to some nonsense. And if we indeed can arrive to a nonsense, it will mean that our wrong assumption was indeed wrong, and therefore the correct assumption is correct. Does it make sense? So we will arrive to some nonsense, and due to nonsense we will agree that original assumption that is not corresponding to this theorem is not correct, and then we will start believing that density determines external potential energy. The proof itself will be residing on the variational principle. variation of theorem. Now, principle. We were briefly touching this subject in lecture number 12, I think, and it is on the D2L. That slides, if you were not in class this day, is on the D2L, and it is also tape recorded. I also was not in class this day, so it was tape recorded through Skype. So the idea of this variational principle is that if we have a big molecular system with many electrons, many ions, and we do know the ground state wave function and ground state energy, then any change in the wave function will provide higher energy than the ground one. So there is nothing strange. It is like more or less common sense statement, but one needs to spell it out rigorously as a step to next developments. So if one has a total energy for ground state, and one does have a wave function for ground state, then expectation value of any wave function that differs from the ground one will provide energy bigger than E sub 0. And the nonsense that we are going to get at the end of our consideration will be that EA plus EB, where both EA and EB are total energy of systems with different situations of the same system. So we are getting inequality in place where one should get an equality. So there are two things defined in the exactly the same way, but assuming that this theorem is wrong, one will get wrong sign. So what is our wrong assumption? So the wrong assumption is that in case we do have an electron density, we can obtain two different external potentials, and therefore we can obtain two different total energies, with understanding that original density was corresponding to ground state. So we are assuming that if our original statement is wrong, then we can get two ground state energies, and they will be not equal to each other. Okay, so by now we do know the theorem and we do have a plan of a proof. So we just need to go across this several logical steps and see that from this point we get to this point. Yeah, here is just maybe better than a handwriting formulation of the theorem and of the proof. So we do have several basic steps to arrive to the final contradiction. So first, we are assuming that first total energy that we have chosen is the true ground state energy. And this HA is a molecular Hamiltonian corresponding to the energy A gives molecular Hamiltonian HA and gives total energy HA. And let's assume that this is correct. True minimal total energy. But also it gives the wave function. Then if we take wave function B, which is not equal to wave function A, then expectation value of a molecular Hamiltonian A with wave function B should be bigger than this originally stated true total energy. Any questions or objections to this point? For me, it was the hardest one. The rest is more technical. So, as the next step, we add and subtract the second Hamiltonian into this expression. So there are no more logical steps until the very end. The rest is more plain with expressions. So if we add and subtract, A plus and minus HB we get a difference of Hamiltonians and we get the psi B H B psi B, which is equal to total energy in the for the total potential B, for the external potential B for Hamiltonian B, for wave function B. So how can we verbalize it? So yes, we allow two simultaneous independent total energies, two streams of connections between density, potential, and energy. This is total energy in the B stream in alternative way of description. This is I'm missing inequality sign here. So those things refer to expectation value. And this inequality sign originates from the variational principle. Okay, it is here. Yes, please. No. Very good. Thank you for asking. So there are two angular symbols in here. So probably it is the only situation when bra and cat are not perfect to use. So here, this is bra, and here, this is cat. Here, it is the sign less, inequality sign. So total energy is less than expectation value of the thing in this bra and this cat. It is not two bra symbols or two less symbols one after another. This is this means less. This one means bra. Make sense? We are speaking about the difference in molecular Hamiltonians. But those are difference in molecular Hamiltonians for the same density, for the same system of electrons, and therefore the difference between molecular Hamiltonians is determined only by external potential. The difference is determined by external potential. We have HA and HB equal to the same kinetic energy plus this electron to nuclei plus electron-electron interaction. And if we subtract them one from another, HA minus HB, then we get kinetic energy cancels, electron-electron interaction cancels. So we do have a summation of VA minus VB. So we are discussing the reconstruction of the potential created by ions based on the density of electrons. And here we see that this difference in external potentials is also corresponding to difference in molecular Hamiltonian. Okay. So if this is correct, then we can take this expression for difference of Hamiltonians and plug it into this expression. Smaller than. Here we are drawing the bra and cat. Bra, cat. Here will be here we have a summation of VA minus VB. And in their original derivation, they make a summation over all electrons. So energy, total energy for branch A is smaller than energy in branch B, and their difference is corresponding to difference in the external potential. Difference in external potential. Here's a little technical addition. So if you do have bra cat with the same wave function, and we are finding an expectation value of operator, then this bra times cat in our expression. Here the bra times cat can be replaced by density rho E R A minus B. So there is nothing new. It is just reformulation, replacing product of wave function to wave function conjugate onto charge density. This is just of one steps used 5 minutes later. Okay, I'm going to forward by one slide, and there I'm expecting to see this expression typed in a more readable way. So we plug in the difference of Hamiltonians, which depends on the difference of external potentials. Then we plug them in and see this expression. So total energy in branch A, total energy in branch B, and here's the difference, integrated difference in external potential. But at the step when we made our original assumption, we just assumed that there are two alternative branches, two alternative total energies. But we do not know which of them is true or correct. So same corrupted logic may lead us to assuming that B is a true minimum. So following the same corrupted logical route, we can derive same inequality, but replacing A to B and B to A. So following from original assumption, it should be permitted. So we are going to take this expression and replace A to B and B to A. And see what happens. So here is the branch A. Here is branch B. So here we see that total energy A is smaller than anything possible. Here we see that total energy B is smaller than anything possible. So they are very similar expressions with only replacements of A and B. So we are just one step from the completing the proof. And this one, actually, this one step consists of two small substeps. First, in our original assumption, we were not telling that we are going to have two charge densities. We have only one charge density, but it wrongly lead to different branches of observable. So this rho sub A and rho sub B are the same. We are going to use this effect that there is only one density, total density for ground state. And then we are going to add together these two inequalities. So in case we are proceeding forward and adding them together, so this one will cancel this one, and this one will cancel this one, right? So anything we do, we are not going to have this index here anymore. So there will be, therefore, the total term with integration will be erased. Then we have a sub a plus a sub b on the left, and a sub b plus e sub a on the right. The long term with charge density cancels. And we have a summation of e sub a plus e sub b. Then this inequality sign, e sub b plus e sub a. And according to designers of the theory, this is a big logical false. So two things determined by the same way should be equal. They cannot hold this inequality. And based on this statement, they conclude that original assumption was not correct. That assuming that same charge density leads to alternative branches of observables is not correct. This is false logical paradox. Same charge density leads to alternative branches of observable. If this is false, then this is also false. This is not correct. And if the charge density doesn't fit to alternative branches, then it means to one and only one stream of observables. And it is what they originally wanted to prove. And we can say that knowledge of total charge density ground state charge density determines one branch of observable. Gives the external potential, total energy, and anything that can follow from this point. Okay, so we did complete this proof. We started from wrong assumption starting from one density, having two branches of energy. We use the variational principle, and then we arrive to the logical paradox. And here we see as our main result that knowing the density automatically, well, not automatically, but potentially provides knowledge of the total energy. So here is the comment that we were talking about at the beginning. So in a normal way of thinking, we are setting positions of ions, positions of nuclei as input, and get energies and densities as output. And here in this theorem, the direction of logic is different. If one knows the density, then one can reconstruct the potential and positions of ions, because electrons keep an imprint of positions of ions, of their attraction by ions in their distribution of density. Okay, I think it is everything for today. When we meet next time, we need to apply another theorem that serves as a background for density functional theories, that the way how the density determines total energy is unique. And there is no theorem how to find this law, this functional, but there is a theorem that such functional exists. There is a existence theorem. And then we'll go to practical implementation and to observables. The practical implementation will be very similar to self-consistent field in Hartley-Fock theory. So it will also have the self-improvement loop. And, in practical part of DFT will be covered in the lab tonight. So I'm open to answer any questions.
Excuse me, Dr. Gillen. In our homework number 6, we had some confusion regarding how to find how many d orbitals are there, and other question as well.
Wait. What? Just repeat. What was difficult to find?
Regarding our homework number 6, we had some confusion, like how to find how many d-like orbitals are there, or other question as well.
Oh, okay.
And it would be better if you can comment on our homework and send it back to us, if you can do that, so that we can understand how.
Okay. Well, I do not promise, but I'll do my best. I'll try.
Okay. Can you answer some of them, like how to?
Well, this question is more to your general scientific and chemical intuition. It is not to knowledge of the procedures. So you do know the shapes of d orbitals, which are this.
Is it just by seeing?
Huh?
Is it just by seeing by yourself?
Yes, just by seeing. So you identify the orbitals localized around the metal ion, and you, by your human perception, analyze that they look either this way or this way, and count how many orbitals do have this character.
Sorry?
There are strict numerical ways to do this analysis, but in this homework, you were relying just on your visual perception.
Oh, okay.
And then you can connect it to expectations based on the atomic physics or inorganic chemistry, so that there should be 5 d orbitals.
Oh.
Okay?
Okay.
Any other questions?
We have lab today?
The lab is in Vermilion at 6 p.m. at the basement of Arts and Science. If you are not able to attend...
Actually, we are not able to do any of the labs.
Yeah, I know. I will be trying to make a protocol of what I'm doing, just typing in a Word file during the instructions, and then distribute it through D2L.
Okay, that is somehow helpful, but we are not kind of getting everything.
Well, feel free to email me and other members of the class.
No problem.
I strongly encourage your intercommunications.
Okay, no problem. Thank you.
Okay, thank you very much.
Thank you.
Class is